Hey, folks. We're continuing our look into particle motion. So we left off. Um, so we've already talked about basically this whole sheet is what I'm thinking of, all the different scenarios. And so let's go ahead and apply that now. A couple of things to note. So what I usually do. Let's read it first. The graph above shows the position y of t of a particle in inches. All right, as we annotate here, leave yourself lots of notes. This is a sad face for me, but I still want to write it down. This reminds me that we've got units. So the position is given in inches, and we've also got time, so we've got units. That means all of our answers have to have units. So the graph above shows the position y of t of a particle in inches moving along a vertical line. So that's kind of interesting. We've got a vertical line going on here, which is probably why they named it y of t instead of s of t or x of t, because we're moving vertically. And this is occurring for all times t. Now, I like to write this up using interval notation. So t is an element of, we're going from 0 until 7 inclusive. Okay, so I always start these off by trying to remember the relationship between position, velocity, and acceleration, and I base it on the equation that I have. So in this case, our position equation is given by y of t. So position, y of t. Then we have velocity, which is v of t, which is going to be the derivative of position, so that would be y prime of t. And then acceleration, which is a of t, which is the derivative of velocity, which is the second derivative of position. Now, what's interesting about this scenario is we don't have equations to go figure out our derivatives. We're going to have to do everything graphically. So if I want to talk about the velocity, I need to talk about the slope of y prime. So I'm going to actually leave myself an extra little note there that this is the slope of y. We can't come up with the equation for velocity this time. We're going to have to figure out the slope. Okay, so let's get after it. So on what open intervals from 0 to 7, open intervals, so notice that we cannot include 0 and we cannot include 7. So that game is over. Whether or not they should be included or not doesn't matter because they've defined our interval, time interval, to be from 0 to 7, not inclusive. When is the particle moving down? So I want to annotate that. When is a particle moving down? That's when our velocity is less than 0. Now, okay, so something I can point out here. If you make this little chart at the top of your problem, you don't have to then keep writing that velocity is the derivative of y. I'm not so sure that I would even worry too much about it, but just in case, v which equals y prime has to be less than 0. My velocity is negative. That means my particle is moving either left or down, and in this case, we're talking about moving down. Okay, so according to our picture, the particle, like I said, I always like to throw it back at them. Just take their question and spin it back around. The particle is moving down. For all times t that are an element of, all right, now we've got to look up above and we've got to figure out what times correspond to a negative velocity. So in other words, what times correspond to the graph having a negative slope? When is y prime negative? So if you look here, our slope is 0. We look here, our slope is negative. Our slope is positive. Our slope is negative. So we have two intervals two intervals in which our slope is negative. So I'd say the particle is moving down for all times t that are an element of. Now remember, we can't include it because of the way they've defined it, so I don't even have to try to think twice about when my particle is moving downward. So I don't have to include that moment, which makes sense considering the derivative does not exist there because we have a sharp turn. But from 2 to 4, union with 6 to 7, don't forget your units, seconds, and then it also said justify. So at the end of your sentence, you always want to say why this is true. Because v of t is less than 0. My particle is moving downward because my velocity is less than 0. On what open intervals, or at what times from 0 to 7, again, we're not including 0 or 7, is the particle at rest. So that would be, when is my particle at rest? That's when the velocity is 0. Don't get confused. Right here, my particle's position is 0. My particle's position is 0. It doesn't necessarily mean that it's that the particle isn't moving. This is moving. The particle is moving, and it's moving from a position to the above 0, through 0, to a position below 0. So we want to figure out, when is our particle at rest? When are the places where our slope is 0? Well, the particle is at rest for all times t that are an element of. So we want to figure out, where is the velocity 0? In other words, where is the slope 0? And we have looks like from 0 to 2, our slope is 0. For all times t is an element of from 0 until 2 seconds. Don't forget your units. Why? Let's justify. Because velocity is equal to 0. Because we made this chart, we can reference velocity. If you wanted to, you could also just write here y prime is equal to 0. At what times from 0 to 7 does the particle change directions? So when does a particle change directions? A particle changes directions when its velocity switches signs. So the velocity switches from being positive to negative, or from negative to positive. So for us, we want to look at where are the places that this graph changes where the slopes change signs. So I'm going to do my write-up a little bit first. The particle changes direction. The particle changes direction at, now these are specific times, so this isn't going to be an interval again, so I don't have to write for all times. All right, so let's see. Now I'm looking at the slopes, and I want the slopes to change signs. Slope is 0, slope is 0, slope is negative. Now my slope didn't change signs. It went from having no sign to being a negative sign, so that does not count as a change in direction. My slopes are negative. My slope is still negative. That just means position is 0. My slope is negative. Then my slope becomes positive. So this is a moment when my particle changes direction. My slope is positive. My slope is negative. This is another moment where my particle changes directions. So we would say the particle changes directions at times t equals 4 seconds and t equals 6 seconds. Because, why? Because velocity switches signs. And if you wanted to write v of t, you could. During the first 6 seconds, what is the particle's displacement? Okay, so let's annotate this. What does displacement mean? There's distance, then there's displacement. Distance is a measure of total distance traveled, where displacement is a comparison of where did you start and where did you end. Displacement can have a sign. So when I want to do a displacement, I take the end and I subtract the beginning. Well, what is the end of my story? So if we're going for the first 6 seconds, the end of my story is y of 6. What is my position at 6 seconds? And I look up above. At 6 seconds, my position, my y value is 0. Then I want to see where I begin. Well, if it's the first 6 seconds, the end of my interval is 6 seconds. The beginning of my interval is 0. If I go up to my graph, my particle's position at 0 is 6. So if I want to figure out the displacement, I would do the end minus the beginning. So that would be y of 6. Take away y of 0, which ends up being 0, subtract 6, which ends up being negative 6. So my particle's displacement is negative 6. Don't forget your units, inches. Now, what does that mean? Explain what this means in terms of the particle's position. Particles change in position. So if I have a displacement of negative 6, that means that I've moved negative 6 units. In other words, I've moved 6 units down in this case because we have a vertical line. So I would say something like this. The particle moved 6 inches down the line in the first 6 seconds. During the first 6 seconds, how many inches does the particle travel? Okay, this gets to be a more interesting question in my opinion, because we've got to figure out now how many times did our particle stop, start, move, change directions, and then we've got to calculate all those individual distances. So, during the first 6 seconds, through how many inches does the particle travel? So we want to figure out what's happening right off the bat. So right off the bat, my position is at rest. My particle is at rest for all times t that are an element of 0 until 2. Now this is just notes. These aren't my answers, so I don't have to put units on them right now. My particle then starts going what would my velocity be? My velocity is negative because these slopes are negative. So my particle goes left until t equals 4 seconds. Left, 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 left. Then it goes right until t equals 6 seconds. Now, I don't want to keep looking. Don't fall for that. Just because the graph keeps going doesn't mean that we want to keep going. You always want to look at the interval that they're talking about. They're talking about the first 6 seconds, so it's a little deceptive that our graph keeps going. We don't care that the particle then goes to the left again after 6 seconds. So we've got to figure out all these distances. So how far did our particle travel when it was at rest? It didn't, right? From 0 to 2 seconds, from times t that are an element from 0 to 2 seconds, we had 0 inches traveled. Then we want to figure out how far did we travel then in those from 2 seconds until 4 seconds. So how far did we travel? T of nope, not t of, y of 2 equals 6. So we know at 2 seconds our particle's position was 6. What was our particle's position at 4 seconds? It was negative 6. So y of 4 is negative 6. And then when else did our particle, then our particle started going to the right until we got to 6 seconds. So that's position was y of 6 equals 0. So what I want to do now is I want to figure out how far apart did we travel. So from 0 to 2, I didn't move at all. So who cares? At 2 seconds, I was at a position of 6. So from a position of 6 until a position of negative 6, I traveled 12 units. Or 12 inches. I don't have to say units here. 12 inches. And then from 4 seconds until 6 seconds, I traveled a distance of 6 inches. The question is, how much did we travel altogether? So I would add those up, and I would say that the particle traveled 18 inches. Notice this doesn't say a justify. This is just asking strictly for an answer. So I can just answer 18 inches. Sometimes it's nice to say the particle traveled 18 inches, but I don't have to here. So let's just pause and kind of go back and make sure this makes sense. So what I did here was I said I had to look at the picture. How far does my particle travel? So I've got to figure out all the spots that it starts moving, and then when it changes direction, and then when it stops. So my particle doesn't even start moving until 2 seconds because its position is at 6. At 6, how far did my particle travel from 0 to 2 seconds? Nowhere. Then from 2 until 4 seconds, my particle is going to the left because I've got negative slopes. So I started at a position of 6. I ended at a position of negative 6. That means I traveled a distance of 12 inches. Then I changed direction there and I started to travel again. Over those next 2 seconds, I traveled another 6 units. So I did 12 units this way. 6 adds up to a total of 18 inches traveled. What is the particle's velocity at time t equals 5 seconds? Explain what this means in terms of the particle's movement. So what do we know about velocity? Well, up above, we already defined this. Velocity is the derivative of position. So it's the derivative of this graph. So if I want to figure out what is the particle's velocity at t equals 5, that means that I want to figure out what is v of 5, which is the same as y prime of 5. I want to figure out what is the slope at 5. So I go up here to my graph, I go to 5, I want to calculate the slope. Now what's nice is this is a line segment, so I can figure out the slope of any 2 points, and that's going to be the same as the slope at 5 here. So let's look here. Be careful, it's not up 2, it's up 6. So I went up 6, I rose 6, and I ran 2. Excuse me. So that means that my velocity is 3. Now I want to put units on this. I got to make sure that I have units because the first question is, what is the particle's velocity? So what I'm going to do is I'm going to box this in as one of my answers, but it's got to have units. So velocity is going to be the change of position over time. So it's the slope of this. So it's the change of position, which is inches over time, which would be inches per second. Now, the second part of the question is explain what this means in terms of the particle's movement. What does our particle then, what does that mean our particle is doing? So remember, particle movement is talking about which direction it's going. And we know that velocity, positive velocity means my particle is moving to the right. Negative velocity means it's moving to the left. Oh, sorry, not in this case. This is up, down, my bad. Positive velocity would be up, negative velocity would be down. So we would say the particle is moving up because I have positive velocity. The particle is moving up the line at time t equals 5 seconds because, why is that true? because v of 5 equals 3 inches per second is greater than 0. What is the particle's velocity at 5.9999 seconds? Okay, so there again, I want to figure out the slope. So the velocity, that would be the velocity of 5.99999 is going to be the slope at 5.999. Now what's nice is at 5.9999999, you're not quite to 6. So that slope is going to be the same as what the slope was at 5 that we just calculated above. So that would be 3 inches per second. What is the velocity at 6 seconds? Now that becomes a little bit more fun, because if I look at what's happening at 6, can you calculate the slope specifically at 6? No, we can't, because what do we have there? We have a sharp turn. So we would say that the velocity at 6 is undefined. Or you could say does not exist, I guess. Probably could get away with that. So just kind of to point that out, this magical particle somehow can be going at 3 feet per second and then magically turn into going negative 3 feet per second instantaneously without slowing down. So I'm not sure physically how this particle could work, but that's the information that we've been given. During what open time intervals is the particle's speed the greatest? So let's take our time here and remember again, what is speed looking at? Speed does not have direction. Velocity has direction. 30 miles per hour is different than negative 30 miles per hour when you're talking about velocity. When you're talking about speed, that's not the case. So remember that velocity, v of t, is equal to, or sorry, speed is the absolute value of velocity, which for us is the absolute value of slope. Okay, during what time intervals is the particle's speed the greatest? In other words, I don't care if the particle is going left or right. I don't care if the velocity is positive or negative. What section has the steepest slope? So the particle that has the steepest slope, okay, so from here, what's my slope? So here, velocity, which is the slope, is 0. In this section, the velocity, which is the slope, is, what would it be? So you'd go down 6 over 1, so it would be negative 6. In here, my velocity, which is the derivative, is equal to, well, we just did that, it was 3. And then in this section, my velocity, which is the derivative, is negative 3. So if I take the absolute value of all these velocities, which number is the biggest? It'd be this one right here. So from times 2 until 4, during what open time intervals is the particle's speed the greatest? The particle's speed is greatest for all times t, an element of, what did we say? From 2 seconds until 4 seconds, not inclusive. Dang it, I said 0. For all times from 2 until 4 seconds. During what open time is the velocity the greatest? Now the velocity is asking for something else. The velocity is asking when strictly Does this have the biggest number? Which slope is the biggest slope? So as I go back up and look here, I've got a slope of 0 and then a slope of -6. So right now, this is my biggest slope. Even though it doesn't move, that would be considered right now the greatest velocity, because this velocity is negative. Oh, and then we got a velocity of 3 here, and then a negative. So the largest number, straight up number of all these, the largest number is 3. So we would say the particle's velocity is greatest for all times t is an element of, okay, so what intervals is that number 3? So from 4 until 6 seconds. 4 until 6 seconds. Now it doesn't have a justify here, so we don't have to feel like we have to justify this. What is the particle's acceleration at time t equals 3 seconds? So let's review. Remember, acceleration is the derivative of velocity, which is the second derivative of position. So if I was looking up here, let's look at time t equals 3 seconds. So at time equals 3 seconds, our velocity is -6. But our velocity is constant throughout from here to here. So at -3, my particle is not speeding up or slowing down. Its velocity is strictly -6. Its acceleration is 0, because that's a constant velocity. That velocity doesn't change from 2 seconds to 4 seconds, which means its acceleration must be 0. It's not speeding up or slowing down. So A of 3, the acceleration at 3 equals 0 since velocity is constant for all times t is an element from 2 to 4 seconds. Okay, here we go. Ooh, this is interesting. Right off the bat, when I look at my picture, well, let's read it. The graph above shows the velocity v of t. So the first thing that I'm going to highlight, note, this is a picture of velocity. This is not a picture of position. This was a picture of position. So now this is a picture of all of the slopes. So now we have a picture of velocity. And then we have acceleration comes after that. Acceleration would be equal to, like I said, I always like to make this chart, v prime of t. And then we are going to talk about position, but I'm going to wait. There's an example down at near the bottom that I'm going to use to explain how position works. So this graph shows velocity. The graph above shows the velocity of a particle in feet per second. Here we go. This means that my answer needs to have units. We're moving along a horizontal line, so that means we're going left, right. I like to organize this as an interval so that I can see it in interval notation. From 0 until 6. And then here we have units again. On what open intervals or at what times is the particle at rest? So when is my particle at rest again? My particle is at rest when the velocity equals 0. So as I look at this picture, I'm looking at where this is the picture of velocity. I want to look at where this picture has a y value of 0. And you see pretty quickly, right there we have a y value of 0. Right there we have a y value of 0. What does this mean? What does this interval mean? Well, if we go back and we take this and turn it back into what we just did, where this is a picture of position, this would mean that my particle's position doesn't change, or its velocity is 0. Well, this is a picture of velocity, so this means that the velocity doesn't change. Now, the velocity is still 4, but it doesn't change. So this means the acceleration is 0. So when we're looking at this, remember that when we take the slopes now, the slopes are going to be acceleration. Okay, so on what open intervals or at what times is the particle at rest? My particle is at rest whenever the velocity is 0. So there's a picture of velocity. I have a height of 0 here, and I have a height of 0 here. Let's call that like 4.2. So the particle is at rest at times t equals 1 second and t equals 4.2 seconds. Said justify, so we got to say why. Because v of t is equal to 0. Now we can reference v of t because we defined v of t up here in this little chart. So if you don't define it, I don't know how picky College Board will be about it. I won't be too picky about it probably, but it's best to just define that right off the bat. On what open intervals is the particle moving to the right? Okay, again, when does my particle move to the right? Pause, take 3, actually I'll just give you 5 seconds. When is a particle moving to the right? A particle is moving to the right when the velocity is positive. So I'm looking up here, I'm looking for when the velocity is positive. Remember, this is a picture of velocity. So I'm looking at all the spots where my velocity function is above 0. So all of these values. So from time 0 until 1, and from time 4.2 until 6. So back down here, the particle is moving to the right for all time t, that's an element of. So now I want to look back up here. At what values is my particle positive? Now this is where it gets a little tricky. If my velocity is positive, my particle is moving to the right. And this time, my interval is included. So this is a picture of velocity. At time equals 0, the velocity is 4. So that means I want to include time equals 0. Now before we didn't include the endpoints, but that's because our interval didn't include them. So we could ignore it. Here we've got to be a little bit more careful. Now our particle is moving to the right for all velocities that are positive. So this is positive, 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 positive. And then at time equals 1, my velocity is 0. So I'm not going to include time equals 1 because that's a velocity of 0, which means it's not moving. Then my velocities are all negative. I can ignore all these, all these, all these. And then at 4.2, again, my particle is at 0, but right after 4.2, my velocity is at 0. But right after 4.2, my velocity is positive. And my velocity is positive all the way until 6 seconds. Don't forget your units. It said justify. The particle is moving to the right for all times t, blah, 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 because velocity is greater than 0 or positive. On what open intervals or at what times from 0 to 6, not inclusive, so that's interesting, is the particle moving at its greatest speed? When is it at its greatest velocity? So just again, I know we just did an example like this, but let's review it again. Greatest speed, absolute value of velocity. Greatest velocity is straight up the largest velocity number. What's the biggest number for velocity? Okay, so what I want to do is I want to look at my graph now, and this is a picture of velocity. So what's the biggest point, positive or negative, that our graph ever reaches? So it reaches a height of 4, it goes down to 0, then it goes down to -6, then it goes back up to 4 and 4. So the biggest velocity number, once we take its absolute value, is -6. So that's when our graph achieves its greatest speed. It doesn't say justify, so that's nice. But let's just write it up. Greatest speed is time t equals, when was it? 3 seconds. Okay, now velocity is asking a different question. What's the biggest positive number? What's the biggest number that we achieve? The highest this graph reaches is a height of 4. So my greatest velocity is at a height of 4. And so when do we reach a height of 4? We reach a height of 4 at 0. And then we also reach a height at 5 to 6. But look, be careful. Our interval does not include 0. So we got to really pay attention to these details. So we can't count 0, even though our graph reaches a height of 4. Our graph reaches a height of 4, so we're only going to count from 5 to 6. I'm going to include 5 because it's in our interval, but I'm not going to include 6 because it's not. So my greatest velocity occur when times for all time t is an element of, I'm going to go from 5 until 6, but I can't include 6 seconds. I'm going to leave myself a little note. Can't include t equals 0. Even though at time t equals 0, we do have a velocity of 4, we can't include it in this case because of our interval that they gave us. On what open intervals or at what times is the particle's speed increasing, or when is it decreasing? So I want to leave myself a little note here. When is a particle's speed increasing? Do you guys remember? It's when acceleration and velocity have the same sign. When is my particle decreasing? When acceleration and velocity have different signs. Okay, so if I'm thinking about this in terms of velocity and acceleration is looking at the slope of velocity. So if I want to figure out where is my particle speed increasing, it's when velocity is positive and the slope is positive. Or velocity is negative and the slope is negative. So I'm looking for those two intervals. Okay, so let's see. If I go down here, I'm going to leave myself a little chart. When is my speed increasing? Okay. So I want my velocity and acceleration to have the same signs. So let's look in here. Right now, my velocity is positive. These are all positive y values. but their slopes are negative. That doesn't count. Those are different. Then in this next section, my velocity is negative and my slope is negative. Now you do have to be careful here. We have this transition right here. I cannot calculate the acceleration at this spot. So we can't, even though this next section, look at the values are negative, the velocity is negative, and the slope is negative. So in this section, velocity is less than 0, acceleration is less than 0. In this section, velocity is less than 0, acceleration is greater than 0. Actually, we should have probably just done this right off the bat. Let's go back up here. In this section, velocity is positive, is greater than 0, but my acceleration, the slope, is less than 0. Then I did these two already. In here, my velocity, my y values, my velocity is negative, but my acceleration is positive. And then in this last section, my velocity is positive, but my acceleration is 0. Those slopes are 0. So if I want to be speeding up, I want to have the same signs. And so we have two sections that have the same sign. So from 1 to 2, I should have looked here. This is its own section as well. Because look at my velocity is negative, then my velocity becomes positive, and my slope is also positive. So what you want to do is you want to look everywhere there's some transitions between a positiveness and negativeness of the y values. So when is my particle increasing? So when is my speed increasing, I should say? My speed is increasing for all time t that's an element of, okay, so no, velocity and acceleration are different. Velocity and acceleration are the same. Velocity and acceleration, dang it, I did that wrong. Sorry. Now, it's tempting to write from 1 until 3, but we can't because we cannot figure out the velocity here. So we would say from 1 until 2 and then 2 until 3. So for all times, 1 until 2, union 2 until 3. Let's see, is that it? Then I go into my velocity is negative, but my acceleration is positive. My velocity is positive and my acceleration is positive. So then also 4.2 until 5 seconds. When is my particle decreasing? So when is my speed decreasing? For all times t that are an element of, okay, so there we go right off the bat. Should I include 4? No, I shouldn't include 4. My velocity is positive here because this is a picture of velocity, but if I tried to get the derivative, I couldn't get the derivative at that spot. So I would not include 0. So for all times 0 until 1 second, don't include it. Union with negative, 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 positive. So I'm going to include that. So that's from 3 until 4.2. And then we've got positive, positive, and then positive 0. So those would be it. What is the particle's acceleration at time t equals 4.8? So acceleration is the derivative of velocity. So I want to figure out at 4.8 what is happening to my slope essentially at 4.8. Now 4.8 is here, so that's going to have the same slope as this whole interval. So I want to figure out the slope of that big chunk first. So I would rise up. That's 6 and then 4, so that's a total of 10. I went up 10. Then my run is over 2. So rise 10, run 2, my slope is 5. So I would say a of 5, my bad, a of 4.8, which equals the derivative of velocity, 4.8, equals 5. Now we need units. So this is a measure of feet per second, the change in this over that. So it'd be feet over second and then another second. So it'd be feet per second squared. So what was the question? What is the particle's acceleration? That's simple. It just wants the acceleration. It doesn't need to justify. But then it does say, explain what this number means in terms of the particle's velocity. So this is a change in velocity. So we would say something along the lines of the particle's velocity is, and I don't like to just say changing again, I like to say increasing or decreasing. Since that's a positive 5, I would say the particle's velocity is increasing by 5 feet per second squared at time t equals 4.8 seconds. This is going to be a little bit longer video than I'm used to. We're already at 45 minutes, but I want to finish these last couple. On what open intervals or at what times is the acceleration of the particle the greatest? So the acceleration, again, let's leave ourselves a reminder here. The acceleration, a of t, is what? It's the slope of velocity. So we want to figure out when is the slope the biggest. Now this is the greatest, so any negative slopes are out, so I can kind of ignore that. So if we look here, what's the slope from here to here? Down 4 over 1, so that's negative. Well, these slopes are all negative, so I don't care about them. Even if they're bigger, it's not saying, well, acceleration always has a sign. So I would figure out where's the largest, the steepest slope. Yeah, it looks like it's that same interval that we talked about. So from 3 to 5 seconds is when we have the biggest. On what open intervals is the acceleration of the particles greatest? The particle acceleration is greatest for all time t from, what would it be, 3 to 5 seconds? And then last but not least, what is the particle's displacement during the first 2 seconds? Okay, so displacement, it's an interesting, displacement is a measure of position. So if I wanted to figure out displacement, I would have to do the end, subtract the beginning of position. Well, we have a problem here. What is our picture of? Our picture is of velocity. So we don't have a picture of position. Well, it turns out to figure out position, we have this thing called the antiderivative. Just like anything in mathematics, we almost anything you could think of in math has something called an inverse. And so the inverse of derivative is this thing called the integral. And some of you who have taken physics maybe have already seen that. And so position is the integral, position x of t is equal to the integral of velocity. It's the antiderivative. Well, it turns out that it's the area under the curve. So if I were to highlight the area under this curve from 0 to 1 second, and I'd add it to the area under the curve from 1 to 2 seconds, if I added that up, that would give me my function's displacement. That's what this means. So if I go down here to the bottom, let's write ourselves a little note that says position x of t is equal to the integral from 0 seconds until 2 seconds of v of t, which is the same as the area under the curve. So in this case, this area would be 1/2 base times height. So 1/2 times 4 times 1 would be 2. This area under the curve would be 1/2 base, which is 1, times -4, which would end up being -2. And if I add 2 plus -2, I end up getting a total of 0. So what is the particle's displacement from 0 to 2 seconds? Well, it's 0 feet. Its overall displacement is 0, which kind of makes sense because look at what's my velocity here? My velocity is positive. What is my velocity here? My velocity is negative. So my particle moves to the right, then it stops, and then it moves to the left and comes back exactly to where it was before. Okay, so that was a little bit longer than what I usually like to do by a couple minutes, but I'm going to come back and we'll do that last page of being able to do particle motion from a table.